in Gauss-Seidel, I have a bunch of grid points, and the update is different. The update is that this grid point now depends on here and here. This grid point depends on here and here. This grid point depends on here and here, right? So the left value is actually the most recently updated value. So if I still split the work in the same way, so let's say I still have a red CPU responsible for this part, and a blue CPU responsible for this part. What happens is that the red CPU now have to wait. The red CPU, in order for me to compute this grid point, it depends on this and this. So the red CPU seems to have to wait for the green CPU to finish before it can start its work, which doesn't make parallel computing. It defeats the purpose of parallel computing, right? Parallel computing is good because multiple workers can work on the same thing at the same time. If one worker has to wait until the last worker finishes his job, then it doesn't make sense to do parallel computing anymore. So what we can say is that Jacobi is a naturally parallel, and Gauss-Seidel is not naturally parallel. So that's one of the disadvantages of Gauss-Seidel. There are methods to overcome that difficulty though. So the key is to reorder the indices. Okay. So in Gauss-Seidel, previously I have numbered the indices in the matrix according to the spatial grid points. Right? So all the neighboring spatial grid points are neighbors in the matrix index. I don't have to. Alright? I don't have to. So the trick is to order the indices in the matrix in a different way. And there is a huge literature in graph theory. Actually, how do you do that ordering? Basically, you assign different colors to different indices, and then order the indices according to these colors. So what you actually do is that you want to make sure that very few adjacent indices in the matrix actually have dependencies. So let me tell you an example. So if I have a matrix like that, 1, 1, 1, 1, I can reorder the indices by taking the first and then third and fifth all the way to the back, and then go back and take the second and fourth. So I first name all the odd indices and then all the even indices. So after that reordering, and basically permute all the rows of the matrix as well as all the columns of the matrix. So after the permutation, the matrix becomes, the diagonal entries is going to be the same, because taking the diagonal entries just with some spacing, I'm still going to get -2s, right? But then this entry becomes 0. This entry becomes 0 because I'm looking at the adjacent. I'm looking at the old matrix, this entry of the old matrix. All right, and then I have a bunch of zeros until I exhausted all these odd entries and come back to this first even entry. So it'll get a 1 over here, and then a bunch of zeros. So this one gets permuted over to some place that is far away in the matrix index. So correspondingly, this one is now here because this is an even row. It gets permuted after all the odd rows are counted. All right. So for the second one, I'm looking at the third row in the original matrix. So I have a -2 here, I have a 1 here, and I have a 1 here. So what I ended up getting is a matrix that is now a 2x2 block. The first block only has diagonal entries. The last block also has all diagonal entries, and I get 2 other blocks on the that are also pretty sparse. Right. So this is just an example of reordering. In reality, not all. So for structured grid, actually you can do this all the time. Basically, this is they call red-black reordering. So all the even indices are called the red blocks. You assign a red color. All the odd indices you assign a black color, right? And that allows you to split the matrix into a 2x2 block, while each of the diagonal blocks are diagonal. Yes.
Are those equal because the rows don't sum up to be equal?
There should be. On
There
the
should be
second
another-
and third, there should be a lower
another
diagonal
row,
also. That's filled there.
There should be 2 diagonals of 1
Yeah.
in both upper and lower.
Let me see. Yeah, that's a good point.
Because there should be 2
Node 3 should
two
be
diagonals.
mapped to node 2 and 4.
Yeah.
It's only mapped to 4 as of now.
Oh yes, there needs to be 2 diagonals. So right. So on here, I have so this is the first entry over here. I have 2. Yeah, I actually have 2 1 0 1. So this row is the second row in the original matrix, right? And the second row has a 1 over here and 1 over here. They actually corresponds to actually the first 2 entries of the first 2 entries of this corresponding row now, because I have permuted all the columns also. So there is also 1 1 here, and at the very end I think I just have a single 1. Over here I have a single 1 to start with, then at the next row I have 2 1s, and third row I also have 2 1s. At the very end I still have 2 1s, right? So that's the new structure of this matrix. Yeah, thanks for correcting me. Right, the key is that you want to reorder the matrix into a block structure where each diagonal block is completely diagonal. Then you can perform the Gauss-Seidel iteration in multiple passes, while each pass works on one of these diagonal blocks. Right, so for example, if you apply Gauss-Seidel to this matrix, the lower diagonal matrix is only this part. So you can complete all the work, compute all the xk plus 1s for the first block without depending on myself, right? So I can compute, so first compute x of k plus 1 I for all the odd i's, right? So that work can be done in parallel for different computers. I'm just going to compute my own odd entries, and then compute xk plus, then communicate. And finally, compute xk plus 1 for even i's. So that's how you do Gauss-Seidel in parallel. In general, if you have an unstructured grid, you have I can't promise you can split all the indices to odd and even numbers and get a matrix that only has diagonals on the diagonal blocks. But it's always possible to split into multiple colors, and the whole field of graph coloring is for doing that, so that there is no adjacent grids that are of the same color, which means the diagonal blocks are just diagonal. All right. Any questions about this? Yes.
Question: what's the interest of Gauss-Seidel with respect to Jacobi? Does it just converge faster?
It converges faster, and in some cases where Gauss-Seidel doesn't converge, in Jacobi doesn't converge, Gauss-Seidel can converge, right? So it converges faster in a lot of cases, and it may converge for matrices where Jacobi doesn't converge. Yeah, so we're actually going to study a particular case where Gauss-Seidel is going to converge. So these are for matrices that are symmetric and positive definite, like the structural matrices you worked on project 3, right? So for example, if you have a symmetric and positive definite matrix, you may have the diagonals to be very, very close to 0. So if that's the case, it's very hard to imagine Jacobi is going to converge, because you are basically inverting very small numbers, and every iteration your error may actually be becoming larger. But Gauss-Seidel can actually be proved to convergence if you have a symmetric positive definite matrix.